On August 31st, 1978, a storm in the Atlantic Ocean reaches sustained winds of 125 miles per hour. The National Hurricane Center assigns it a name, Ella, Category 4, and it is tracking northeast, directly toward New York City. At that precise moment, inside the walls of the 59-story Citicorp Tower at Lexington Avenue and 53rd Street in Midtown Manhattan, small electronic devices called strain gauges are measuring the structural stress on the building's steel joints in real time, 24 hours a day, 7 days a week, reading every gust, every shift, every vibration the tower experiences as it stands above one of the densest urban grids on Earth. The strain gauges are there because William Le Mesurier put them there. He put them there because he needed to know, at every moment of every day, whether the storm that was coming was the storm that would kill his building. Not damage it, not crack it, kill it, take it down. All 59 stories. Onto Lexington Avenue, onto 53rd Street, into the buildings surrounding it on every side. The strain gauges tell him what is happening to the joints. What they cannot tell him is whether the power will stay on. And if the power goes out, in the kind of storm that Hurricane Ella is becoming, the tuned mass damper at the top of his building stops. And the moment the tuned mass damper stops, the probability of collapse is no longer 1 in 50. It is no longer 1 in 16. It becomes something that structural engineering does not express as a probability. It becomes a mechanical outcome. Given the right storm, given a power failure, given the joints as they existed before the welders got there. The building falls, not might fall, falls. Hurricane Ella is off Cape Hatteras. The welders are not finished, and the 3 weather services that Le Mesurier has on retainer, providing him forecasts 3 times a day, every day, for exactly this scenario, are all reporting the same track. That is the beginning. This is the rest of the story. Here is what the 2025 Greenberg book reveals that the 1995 New Yorker article did not. In 2025, attorney and historian Michael M. Greenberg publishes The Great Miscalculation, the race to save New York City's Citicorp Tower through NYU Press. He does not work from the same sources that Joe Morgenstern used in 1995. He works from something different. He works from the original file. The Project Serene file, labeled Special Engineering Review for events no one envisioned, that William Le Mesurier kept throughout the 1978 crisis, which sat for decades at Harvard University's Graduate School of Design in Le Mesurier's personal papers. Greenberg also obtains Morgenstern's original interview transcripts from the 1995 New Yorker reporting, the notes behind the article, the quotes that did not make the final edit, the conversations that shaped the story the engineering profession taught for 30 years, what Greenberg finds, and what the Engineering News Record, Architectural Record, and the American Society of Civil engineers all note in their 2025 reviews, is a story considerably more complicated than the ethics lesson it became. Le Mesurier helped hide the nature of the repairs, not just from the public, Greenberg finds. He helped hide them from ENR itself. The Engineering News Record, the primary trade publication of the structural engineering profession. The publication that would have been the natural outlet for exactly this kind of disclosure. The disclosure that never came. The profession that taught the case as a lesson in honesty was itself kept from the full truth. And the file at Harvard contains it, all of it. This is the story of what that file actually contains. Start in 1974, a construction site at Lexington Avenue and 53rd Street, Manhattan. A small Lutheran church called St. Peter's sits at the corner of the block. It will not move. The developer building this skyscraper above and around it has accepted that condition. The structural engineer tasked with solving the problem of building a 59-story tower without touching the church's corner lot is William Le Mesurier, 51 years old in 1974. Professor of structural engineering at Harvard, one of the most decorated structural engineers in the United States. His solution, placing the 4 primary columns at the midpoints of each side rather than the corners, then cantilevering the building outward in every direction from those 4 central stilts, is an engineering breakthrough. It allows the building to hover over the church's corner entirely. It produces a tower that looks unlike any other structure on the Manhattan skyline, and it demands a wind bracing system unlike any other previously built at this scale. Le Mesurier designs a chevron brace system, large diagonal V-shaped steel elements stacked in tiers through the building's full height, transferring lateral wind loads from the upper floors down to the 4 midpoint stilts. The system works because each joint transfers load with precision. The specification for those joints is welding, continuous metallic bonding across the full surface of the connection. Maximum load transfer, maximum structural certainty. During construction, Bethlehem Steel, the fabricator, requests a substitution, bolted joints instead of welded. The cost saving, $250,000. The load values used to design the bolted joints come from Le Mesurier's own Cambridge office. They are the load values for the wind direction the New York City Building Code requires. They are not the load values for the wind direction the building's unique geometry makes its actual worst case. No one in the construction chain connects those two facts. In October 1977, Citicorp Center opens, the 7th tallest building in the world, the first skyscraper ever to incorporate a tuned mass damper, a 400-ton concrete block suspended at the 63rd floor on a frictionless oil film, connected to pneumatic springs, calibrated to absorb the building's lateral oscillation in wind. It is a technological achievement. It is also a system that requires electricity to operate. 12 months later, Le Mesurier knows things about both of those facts that he did not know on opening day. Here is what the opening day celebrations do not explain. There are two numbers at the center of the Citicorp Tower story, 1 in 50 and 1 in 16. They are the same building, same tower, same joints, same geometry, same design flaw, two different probabilities. The difference between them is a single system, the tuned mass damper. Here is how the math works. The tuned mass damper is designed to cancel the building's natural oscillation period of approximately 6.7 seconds. When a wind load excites the building at that frequency, the 400-ton block swings against the motion, 90 degrees out of phase, absorbing the kinetic energy that would otherwise accumulate in the structure. With the damper operating, the effective structural demand on the chevron braces is reduced. The storm threshold that would push the defective bolted joints past their failure point is higher. Engineers calculate it at once every 50 years, 1 in 50 per year. Now remove the damper, which is what happens the moment power fails, which is what happens in a severe storm, which is precisely what happened during the Northeast power outages that were common in 1970s New York. Without the damper, the structural demand on the chevron braces under quartering wind loads is not cushioned. Every gust translates directly into stress at the bolted connections. The threshold drops from once every 50 years to once every 16 years, 1 in 16 per year. But here is the number that neither figure fully captures. When the threshold storm arrives, when the quartering winds exceed 70 miles per hour, when the power fails, when the damper stops, the outcome for the bolted joints is not probabilistic. The probability has already been expressed. The storm has already arrived. The damper is already off. The joint is already loaded beyond its design capacity. What happens next is physics, not likelihood, not risk, physics. The bolt yields, the joint slips, the chevron brace loses its connection. The load it was carrying redistributes to adjacent braces. Those braces were not designed to carry additional load. They approach their limit. They yield. The cascade continues upward and outward through the chevron system. Progressive collapse. 59 stories. Lexington Avenue. 200,000 people in the 10-block radius. Zero probability involved once the storm is there and the power is gone. 100%. Stop here. Because what a structural bolt actually does under an eccentric load, and why the difference between a welded joint and a bolted joint is not a minor substitution, but a fundamental change in how force moves through a building, is the part that explains why a $250,000 cost saving became the most expensive structural secret in Manhattan's history. Here's what happens inside a welded connection when load arrives. Welding melts the steel of both members and lets them resolidify as a single piece. The load path is continuous. Force travels through the joint the way water travels through a pipe, without interruption, without concentration, distributed evenly across the full area of the bond. The bolt is different. A bolt is a discrete mechanical fastener. It holds two pieces of steel together at a single point. When load arrives at the joint, it does not distribute across a surface. It concentrates at the bolt. The steel plates on either side of the bolt develop leverage. The bolt, sitting at the center of that leverage, experiences a force much larger than the applied load, because the geometry of the plates multiplies the demand at the fastener. Engineers call this prying action. It is not a subtle effect. In a joint designed for welding and substituted with bolts, using load rather than the bolt geometry, the prying action produces stress at the fastener that the design never accounted for. Now apply a quartering wind to the Citicorp tower. The wind hits the corner between two midpoint stilts. It loads the chevron braces diagonally. The braces transfer that diagonal load to the bolted joints at their ends. The bolted joints experience prying action. The prying action multiplies the demand at each fastener. The fasteners were sized for a different load, a different direction, a different geometry. They were sized for perpendicular winds, as the 1970 New York City building code required. Not for quartering winds, not for the specific structural geometry that made quartering winds the actual worst case for this specific building. Under a storm of sufficient magnitude, the bolt does not bend. It does not warn. It does not creak or groan or give visible notice that it is approaching failure. It shears, cleanly, in a fraction of a second, and the brace it was holding is no longer connected to the building. That is what the strain gauges mounted on the Citicorp tower's steel joints in the summer of 1978 are measuring around the clock. how close each joint is to the moment it shears, and that is why Le Mesurier is watching 3 weather services report on Hurricane Ella 3 times a day. The welding crews work from 8 p.m. to 4 a.m. every night of August and into September 1978. They enter through a service access. They remove the interior wall panels that cover the structural joints. They grind the surface of each bolted connection. They apply the 2-inch steel plates. They weld the plates over the bolt pattern. They reinstall the panels. They are gone before the first commuter arrives for work. The 50,000 people who work in the building every day walk past walls that were opened 4 hours before they arrive. The wall panels look untouched. The welds behind them are still cooling. The welding contractor is Carl Koch Erecting Company, the original steel fabricator that had worked on the building's construction. They know exactly where every joint is. They know how to access them. They know how to restore the panels so that nothing looks different in the morning. Le Mesurier installs the strain gauges not just to monitor the building. He installs them to know, in real time, whether he needs to make a call. The call that would activate the evacuation plan, the 10-block radius, 200,000 people, coordinated between Le Mesurier, the NYPD, the New York City Mayor's Office, and 2,500 Red Cross volunteers who are on standby, who have been briefed, who know what they are waiting for, who are ready to move, without knowing publicly why. On September 1st, 1978, Hurricane Ella reaches its peak intensity off the North Carolina coast, 125 miles per hour. Category 4. The National Hurricane Center has issued a hurricane watch for the Outer Banks. The storm track in every model points northeast, toward New York. Le Mesurier later says, "We were sweating blood and water." The evacuation plan is reviewed. The NYPD is on alert. The Red Cross volunteers are on standby. The strain gauges are transmitting. The 3 weather services issue their reports. All 3 show the same thing. Ella has gone stationary. Somewhere off Cape Hatteras, the storm stops moving for approximately 24 hours. And then it turns northeast, out to sea. Away from New York, away from the partially repaired joints on the floors the welders have not yet reached. Away from 200,000 people who do not know their names are on an evacuation list. Le Mesurier describes the morning after the storm turns as the most beautiful weather he has ever seen. The welders go back that night, and the next, and every night through October 1978. The final plate is welded in October. The building that would fall in a specific storm is now a building that can withstand the worst storm New York City is likely to see in 700 years. The strain gauges come down. The Red Cross volunteers stand down. The evacuation plan goes into a file. The file is labeled Project Serene, and the file goes into an archive at Harvard University's Graduate School of Design, where it sits for decades, until Michael Greenberg reads it. Here's what the file at Harvard does not explain on its own. The Project Serene file contains the engineering calculations, the repair timeline, the communications between Le Mesurier, Citicorp's executives, the city officials, and the legal team at Northbrook Insurance. What the file captures, and what Greenberg documents in The Great Miscalculation, is the deliberateness with which the information architecture of the crisis was designed. Not just who was told, who was not told, and why. The engineering news record, the publication that, in any other scenario, would have been the natural recipient of a disclosure about a structural failure and secret repair of the 7th tallest building in the world, was not told. Not in 1978, not in 1979, not through the 1980s or into the 1990s. When the ENR eventually covered the story after the 1995 New Yorker article, it was working from what Le Mesurier chose to say in that forum. Not from the file at Harvard, not from Morgenstern's original transcripts, not from the full record of what was decided in the rooms where the decisions were made. Greenberg's reading of the material, reviewed by ENR itself in April 2025, produces a conclusion that the magazine states directly. The narrative in the 1995 article diminishes some, but not all, of the honor associated with Le Mesurier's painstaking admission of fault. The hero story, ENR concludes, is more complex than the hero story. Le Mesurier died in 2007 at age 81. He never gave an interview from the full file. The full file became public in 2025. Both things are true about the Citicorp Tower. By any measure of structural engineering ambition, it is one of the most genuinely innovative buildings constructed in New York City in the second half of the 20th century. 4 midpoint stilts carrying a 59-story tower, 9 stories above street level. A cantilevered structure hovering over the corner where a small Lutheran church refused to yield. A chevron diagonal brace system that had never been deployed at this scale in the American market. The world's first tuned mass damper installed in an occupied skyscraper. a 400-ton concrete block calibrated to swing against the building's natural oscillation period of 6.7 seconds, reducing the structural demand on the bracing system in every wind event from the day it was commissioned. A tower that opened in October 1977 to universal praise from architecture critics and structural engineers alike. A building that still stands today at 601 Lexington Avenue, its angled crown immediately recognizable from any approach to Midtown Manhattan. And it is also a building that, for the first 11 months of its occupied life, would have fallen, not probably, but mechanically, if a storm of sufficient magnitude had hit Manhattan during a power failure. A building whose critical structural connections had been changed from welded to bolted during construction for $250,000 in savings. Without a recalculation of the changed joint behavior under the wind direction, the building's unique geometry made its actual worst case. A building repaired in complete secrecy by overnight welding crews, while 50,000 occupants worked inside it by day, while strain gauges monitored the joints in real time, while 2,500 Red Cross volunteers waited on standby, while 3 weather services filed reports 3 times daily to a man who was watching a hurricane approach the half-finished repair. A building whose engineering file, labeled Special Engineering Review for events no one envisioned, sat in a Harvard archive